hundreds of light years away from us. There exist worlds where life is an unthinkable concept, where the laws of physics act as brutal death sentences, ready to crush, incinerate, or tear apart anything that dares to cross their boundaries. This is a confrontation with terrifying hellscapes deep within the universe. Worlds like Kelt 9b. With surface temperatures and ultraviolet radiation from its host star, so extreme that the planet's atmosphere itself is being melted and stripped away. Set foot here, and your body would be reduced to atomic vapor in a single breath. Or WASP 76b, a planet tidally locked to its host star, where temperatures reach around 2,300 degrees Celsius. Here, iron doesn't merely melt, it evaporates into the atmosphere, condenses on the night side, and falls as blazing rain of liquid metal. And there are many more places that embody the most merciless realities physics can create. Could a human survive even a single second on these extreme worlds? Join us as we begin a journey of exploration into the most terrifying planets ever discovered in the depths of space. If there is an absolute boundary at which all forms of life must come to a halt, that boundary is temperature. This is not the kind of heat that merely causes pain as it does on Earth. On some exoplanets, heat does not simply kill biology. It dismantles atomic structure itself, rendering everything familiar to humanity meaningless. Kelt 9b represents the most extreme example modern science has ever observed. It is an ultra-hot Jupiter orbiting an A-type star that is larger and hotter than our Sunday. Because of its extremely close orbit, the planet is heated to daytime temperatures of around 4,300 degrees Celsius, hotter than the surfaces of many red dwarf stars. Iron and titanium elements that only melt at thousands of degrees Celsius on Earth exist here as gases, mixed into the atmosphere the way oxygen or nitrogen is on our planet. With chemistry effectively disabled, if a human body existed only as a physical hypothesis approaching this surface or atmosphere, it would not have time to feel pain, to decompose, or even to turn to ash. But Kelt 9b is not the only world where temperature defies human intuition. WASP-76b presents a different vision, slower, yet far more haunting. This planet is tidally locked, meaning one hemisphere permanently faces its star, bathed in relentless light and heat, while the other remains in eternal night. On the day side, temperatures are high enough for iron to evaporate, becoming metallic vapor in the atmosphere. Observations and spectroscopic models show that this iron vapor is carried by atmospheric winds toward the night side. There, temperatures drop enough for it to condense and fall as liquid metal rain. No protective material could exist, because all materials obey the same physical law. When thermal energy exceeds electromagnetic bonding forces, structure collapses. Planets like Kelp 9b and WASP-76b force us to reconsider how we define life. On Earth, we are accustomed to placing biology at the center cells, DNA, liquid water as the standard. But here, the limit is not whether organisms can adapt, but whether physics itself allows matter to exist in complex forms at all. When we look at these extreme exoplanets, we do not merely see places we cannot set foot on. We see the fragile boundary that makes Earth possible. The thermal stability that allows liquid water, complex chemistry, and biology is not a given, but a rare exception within the vast architecture of the universe. Shift in orbit slightly, increase stellar energy just a little, and everything familiar can vanish. If temperature is destruction driven by energy, then pressure is destruction driven by mass and gravity silent, relentless, and unforgiving. It needs only to compress space itself, forcing atoms so tightly together that familiar states of matter, solid, liquid, gas lose all meaning. In such worlds, death occurs when structure no longer has room to exist. One of the clearest examples is 55 Cancri, a super-Earth orbiting its host star at a distance of only a few million kilometers, completing a full orbit in less than 18 hours. With a radius about 1.9 times that of Earth and a mass nearly 8 times greater, its surface gravity is significantly stronger than that of our home planet. Planetary structure models indicate that 55 Cancri E has an unusually high density, suggesting a carbon-rich composition that may include exotic crystalline forms such as graphite, carbides, or, according to earlier hypotheses, diamond deep within its mantle. Both the internal pressure and the atmospheric pressure of this planet lie far beyond anything experienced on Earth. Under these conditions, matter no longer follows familiar mechanical rules. Many substances enter supercritical states where the distinction between solid, liquid, and gas disappears. If a human body were to encounter such an environment, what happens would not resemble being crushed in a mechanical accident. Pressure would permeate every atomic gap, compressing soft tissue, bone, and cells simultaneously. This is death by the absence of space itself, not by injury or burning. But pressure is not only a story of rock and metal. It also rewrites the behavior of the most familiar substances, including water. This is vividly illustrated on Gliese 436b, a planet roughly the mass of Neptune, orbiting close enough to its star for ambient temperatures to reach several hundred degrees Celsius. On Earth, water at such temperatures would exist as vapor. On Gliese 436b, however, immense pressures in the deeper layers, again reaching tens of gigapascals, force water into an entirely different state, Ice 7. Ice 7 is a crystalline phase of water confirmed in high-pressure laboratory experiments and predicted to be widespread inside large planets. Water freezes while carrying enough thermal energy to cook any form of biology. This is not cold ice, it is pressure ice, where crystalline order is maintained by compression rather than low temperature. If you were to stand on a layer of Ice 7 like this, you would feel no slipping or melting. Instead, pressure from every direction would squeeze your body inward. Heat would not need to increase. Pressure alone would be sufficient to destroy biological structure. Here, life does not lose to energy, but to density itself. Worlds like 55, Cancri, E, and Gliese 436b demonstrate that pressure may be a fundamental limit to life, equal to or even exceeding temperature. On Earth, atmospheric pressure is only about 101 kilopascals, a value so small that we rarely even notice its existence. In the universe, however, pressure can increase without bound as mass and gravity rise. When that happens, it becomes a dominant force, determining whether matter can sustain complex structures at all. Pressure does not need violence to destroy no sound, no light, only a change in a few planetary parameters, not through catastrophe but through pure physical law. And life as we know it loses the ability to exist. And there is something even more terrifying in a very different way, a form of death that cannot be seen, where mere existence alone is enough to be erased. TRES 2b, the exoplanet recorded as the darkest ever known, reflects less than 1% of the starlight that reaches it, darker than coal or even engineered black velvet. In such an environment, the human eye becomes almost useless, yet the darkness of TRES 2b is not what kills you. It is merely a veil concealing the true threat, radiation. TRES 2b orbits extremely close to its host star, exposing it to a constant stream of high-energy radiation, especially intense ultraviolet light. On worlds like TRES 2b, extreme temperature is not required, nor is crushing pressure. All it takes is a continuous flow of high-energy photons passing through living matter, and death does not arrive as a violent event, but as a silent erasure of biological order. If TRES 2b represents darkness and radiation around sun-like stars, then planets orbiting red dwarf stars reveal an even more brutal scenario. Red dwarfs are the most common stars in the Milky Way, yet they are also infamous for their violent flare activity. Flares from red dwarfs can release X-ray and ultraviolet energy hundreds of times greater than anything Earth has ever experienced during its strongest solar storms. Models show that without a strong magnetic field and a thick atmosphere, this radiation can strip a planet's atmosphere away within just a few 100 million years, leaving behind a barren world. Even more extreme are planets orbiting pulsars, the remnants of stars that have exploded as supernovae. Pulsars emit narrow but extraordinarily powerful beams of radiation, including gamma rays and X-rays, sweeping through space like cosmic lighthouses. This radiation is strong enough to penetrate meters of material, directly shattering atomic and molecular structures. In such an environment, there is no meaningful concept of shielding. Even thick metal can only slow the energy, not stop it. Simply exist long enough in such an environment, and material and biological order are eroded from within. On a philosophical level, worlds like TRES 2b, or planets orbiting red dwarfs and pulsars, pose a chilling question. Can light, something humanity associates with life and awareness, become an invisible executioner? There are places where the atmosphere itself becomes a weapon, where wind is no longer the movement of air, but streams of matter moving fast enough to tear apart anything they touch. HD 189,733b is roughly the size of Jupiter, yet it follows an extraordinarily tight orbit, completing a full revolution around its host star in just about 2.2 Earth days. That short distance exposes the planet to immense stellar radiation, creating an extreme temperature contrast between its day side and night side. This contrast is the driving force behind one of the most violent atmospheric systems ever observed. Aerodynamic models and spectroscopic data indicate that winds on HD 189,733b can reach speeds many times faster than the speed of sound on Earth. At such velocities, air becomes a supersonic flow, carrying kinetic energy powerful enough to destroy matter. The intense heat causes silicate compounds, materials that form sand and glass on Earth, to vaporize, then condense into ultrafine particles as they are swept into cooler regions. These particles do not fall straight down like ordinary rain. Instead, they are driven sideways by the wind, producing a phenomenon often described as glass rain. In such an environment, any surface exposed to this atmosphere would be eroded almost instantly. Even the most advanced protective materials ever engineered by humanity would survive only for meaningless moments before being completely destroyed. If a human body were to approach this environment, death would not come from lack of oxygen or extreme heat. What is most terrifying is that a lethal atmosphere requires only enough density, enough speed, and enough solid material. On Earth, the strongest winds ever recorded reach only a few hundred kilometers per hour, and we consider those rare disasters. On HD 189,733b, supersonic winds are the normal state, with no calm season and no moment of rest. The sky is perpetually in attack mode. A lethal atmosphere shows that a planet can kill everything, even while still retaining a surface, gravity, and a fully intact planetary structure. When we look back at Earth, the fragility of our living environment becomes clearer than ever. Our atmosphere exists within an almost unbelievable window of wind speed, fast enough to redistribute energy, yet slow enough to avoid turning air into a weapon. That balance is not the rule of the universe, but a rare exception. HD 189,733b reminds us that on most worlds, death does not arrive through rare catastrophes, but through conditions that are constant and unavoidable. And even if a planet escapes a lethal atmosphere, no supersonic winds, no glass rain, there are still places where matter is not only compressed, but continuously stretched and torn apart by the overwhelming gravitational forces of a nearby star. WASP-103b is a planet that completes a full orbit in roughly 22 hours, shorter than a single day on Earth. At that distance, WASP-103b lies extremely close to the Roche limit, the threshold at which a celestial body can be torn apart by the tidal forces of the larger object it orbits. Optical observations and gravitational models show that WASP-103b no longer maintains a spherical shape, instead being stretched into an elongated ellipsoidal form aligned toward its host star. Its radius is unusually large relative to its mass. This process generates what is known as tidal heating, with the consequence that the planet's outer layers can never remain stable. If any surface exists, even momentarily, it is quickly bent, reshaped, and ultimately broken apart. In this context, the idea of a landing becomes almost absurd, with no fixed ground to stand on and no stable frame of reference to navigate by. The entire planet vibrates as if locked in a permanent earthquake, but with no epicenter and no end. What is striking is that WASP-103b demonstrates how tidal forces alone, even without considering temperature, are sufficient to turn a planet into a completely hostile world. At a deeper level, tidal forces raise an existential question. Does lasting existence require not only matter and energy, but also a delicate balance among the fundamental forces of the universe? On Earth, we live on a planet with a stable orbit, far enough from massive bodies to avoid global deformation. That stability is often taken for granted, yet in the context of thousands of known exoplanets, it stands out as a rare exception. Tidal forces also reveal that destruction does not have to arrive through sudden catastrophe. With an orbit that is close enough and a host star that is massive enough, a planet can slowly destroy itself through its own gravitational relationship. Gravity, the force that binds celestial bodies together, is also the force that can tear them apart when conditions become extreme. And even if a planet is fortunate enough to avoid tidal tearing, preserving its shape and structural stability, the threat is still not over. GJ-1214b is an exoplanet located about 48 light-years from Earth. It is commonly classified as a mini-Neptune, a type of world that falls between rocky planets and gas giants. Spectroscopic observations of its atmosphere reveal that GJ-1214b is wrapped in a thick envelope rich in hydrogen and helium, mixed with water vapor and other light compounds. Unlike Earth's atmosphere, which is only about 100 kilometers thick before fading into near vacuum, GJ-1214b's atmosphere may extend for thousands of kilometers, occupying a significant fraction of the planet's radius. This is an ocean of gas, where the boundary between atmosphere and planet is nearly erased. As you approach GJ-1214b from space, there is no clear surface waiting below. There is no sharp horizon, no final cloud layer signaling ground. Instead, you descend into gas that grows steadily denser, where density increases continuously with depth. The deeper you go, the pressure rises exponentially, with no natural stopping point. There is no moment of touchdown. If a probe or a hypothetical human body were to enter GJ-1214b's atmosphere, it would not land. It would sink endlessly. Drag increases, motion slows, but never fully stops. There is only prolonged descent through an environment that becomes ever denser, hotter, and heavier. Deeper still, the combined effects of heat and pressure destroy all familiar forms of matter. Death here does not arrive as a sudden shock, but as the complete absence of equilibrium. What makes GJ 1214b terrifying is not violence, but infinite depth. Everything simply becomes denser, heavier, and more hostile, until matter itself can no longer retain its original identity. From a planetary science perspective, worlds like GJ 1214b pose a profound challenge to the idea of habitable planets. They may not be extremely hot, torn apart by tides, or scoured by supersonic glass rain. There is no surface, no familiar geological cycle, no clear boundary between environment and planet. The universe shows us that most worlds do not follow that structure. A solid surface, something we assume to be normal, is, in fact, a rare exception. Even with the most advanced technology imaginable, this scenario offers no escape. There is no material that can anchor itself within a gas ocean where pressure rises without limit. There is no engine that can oppose planetary gravity for long without consuming energy beyond all realistic bounds. And even if a planet does have a surface, a foundation, and a place to stand, the threats do not end there. There are worlds where light nearly disappears, where radiation penetrates every material, and where death comes simply because you exist long enough in the wrong environment. Setting foot on the most hostile exoplanets is not merely an act of space exploration, but a direct confrontation with the most extreme limits of physics and chemistry. On worlds where atmospheric pressure can crush atomic structures in an instant, or where molten metal rains fall from chemically charged clouds, the very concept of life is completely erased. The very existence of these so-called cosmic hellscapes challenges every traditional theory of planet formation, forcing us to redefine how matter can endure under the immense energy released by their parent stars. Yet it is precisely within this suffocating harshness that science discovers its most fundamental values of knowledge. Each terrifying exoplanet is a unique natural laboratory where we can observe physical processes that would never occur on Earth, allowing us to decode the origins and evolution of entire planetary systems. These hypothetical journeys into the hearts of lethal celestial bodies are not meant to search for a new home, but to reveal how astonishingly rare life truly is. Ultimately, confronting the terror of exoplanets is not only about understanding destruction, but about helping humanity grasp its own position, small beings striving to decipher the map of a vast and mysterious universe. Thank you for staying with WUFO Space until the very end of this journey through the vast universe. If you found this video interesting and insightful, don't forget to like, share, and subscribe to WUFO Space so you won't miss our next cosmic adventures. Your support means the world to us and fuels our passion to keep exploring the wonders beyond.